So we've been talking about how we can place complex numbers in a geometrical way, so on the Argand diagram. Now we've seen that they all can be represented as vectors. And of course the advantage of vectors, there's Z, but the advantage of using a vector is I can move it around, I can translate it. And when we translate it, it retains the length, it retains the angle. And then of course were the two key properties of our complex number. So unlike the point, I can't move, because as soon as I just move the single point, it becomes a new number. Move the vector, it still is the same complex number. In fact, look, I'll move it over there to a third position. Still the same. Doesn't matter where you put it. Oh, hours of fun. Just move it around. If ever you want to work out what complex number it's representing, easy when it's joined to the origin, because you just read off the point at the other end. But when we move it round, head minus tail. That'll always tell you which complex number it's representing. All right, so adding and subtracting. Really, it's just adding and subtracting of vectors, because we now call them a vector, and we saw that before. So there's Z1, there's Z2. We know that if we add them, we put them head to tail. So there's the blue one there, and the green vector is Z1 plus Z2. And you can do it in any order. I could have gone the red one plus the blue one, or the blue one plus the red one. We still end up in the same spot. Subtraction, that ends up being the other diagonal in our shape. Just to prove that, Z1 minus Z2, so if I add the negative blue vector, I'd end up down there. And so that black vector there would be Z1 minus Z2, which I could then slide up, and it's the other diagonal. Also, remember we said head minus tail? So the diagonal, I can see that it's going to be Z1 minus Z2. Or it could be Z2 minus Z1, depending on which direction our vector's going there. Triangular inequality. It's a very simple little property. But in any triangle, a side is going to be shorter than the sum of the other two sides. That's basically what the triangle inequality says. So if I've got a triangle ABC, then AC would be less than or equal to AB plus BC. But now if I talk about that in terms of complex numbers, it means the modulus of Z1 plus Z2, which is representing the green one, so that's one side of the triangle, that's going to be less than the sum of the modulus of Z1 plus the modulus of Z2, because they would represent the other two sides of a triangle. But also, it'll end up being bigger than the difference of the other two sides, because you could rearrange that inequality. And I could rewrite it as AC minus AB is less than or equal to BC. So I could say the modulus of Z1 plus Z2, when I'm talking about complex numbers, is going to be bigger than the modulus of Z1 minus Z2. Notice I put absolute value signs around that, because I don't know which side is going to be bigger, Z1 or Z2. No. Equality will happen, because we're saying less than or equal to, if the 3 points are all in a straight line. So it's not actually a triangle. Okay, here's a very old question now. 1995, presented with this particular diagram, and you had to show that the modulus of Z minus W was less than or equal to mod Z plus mod W. So again, it's just using the idea of the triangle inequality. So you say, well, if I join P and Q up, I know that's going to be Z minus W, because we were told OP, where is it? There it is. OP represents Z, so I know its length is the modulus of Z. We were told OQ represents W, so its length is the modulus of W. And the diagonal is head minus tail, so that'll represent the modulus of Z minus W. So by our triangle inequality, we can say, well, righto, modulus of Z minus W must be less than or equal to modulus of Z plus the modulus of W. Now, construct the point R representing Z plus W. Well, that in itself is not too hard, because we just complete the parallelogram, if you like. So we add our two vectors together, and there it is. The point R up there would represent Z plus W. But the more interesting part of the question is what can be said about our quadrilateral OPRQ. And I think by me saying the way I did, I've already said the answer, haven't I? because I said, oh, we'll create a parallelogram. Okay, so we end up with a parallelogram because we know the opposite sides are parallel, or opposite sides are equal in length, whichever way you want to say it. Okay, but we'll take it a step further. If mod z minus w is equal to mod z plus w, what can be said about w divided by z? Well, z minus w, z plus w, they're representing the diagonals. So we're now saying we've got a parallelogram where the diagonals are equal. What does that make our parallelogram? Got to be a rectangle. Okay, so there we go, rectangle. Now, other things we know about rectangles. Well, the one I'm interested in is that the vertex will be 90 degrees. So if you look back on that diagram, the argument of w minus the argument of z would in fact be the vertex of the rectangle. We now know that's 90 or pi on 2. Play around with the arguments here. Remember, when we subtract arguments, we can bring it together in a division. So we're now saying the argument of w on z is pi on 2. I can now say something about the answer w over z. I know its argument's pi on 2. Well, any complex number where the argument is pi on 2, got to be purely imaginary. Purely imaginary. All right, multiplication. All right, we've seen this. Modulus of z1, z2 will be modulus of z1 times the modulus of z2. And when it came to the arguments, we add the arguments. So if I want to multiply two complex numbers together geometrically, what does this mean? Well, let's write it out. R cis theta 1 times R2 cis theta 2 ended up being R1 R2 cis theta 1 plus theta 2. So if we multiply z1 by z2, what's happening to the vector? Well, we've added on the angle theta 2, so we've rotated it theta 2, and that would be in an anti-clockwise direction. And the length of it has been multiplied by whatever the length of R2 was, whatever that is. Okay, so using this diagram, so we're going to rotate z1 by cis theta. Now, the first thing that tells me is the length of the vector is not going to change because I'm multiplying by 1 cis theta, so I haven't affected the length. But I've rotated it theta. Now, that brings up the important point of if we multiply by I, and I is cos pi on 2 plus I sin pi on 2, it must be a rotation of 90 degrees. And in the anti-clockwise direction, of course. Don't forget, I know I've said it a lot, I'll say it again. Head minus tail, head minus tail. Whenever you want to work out what the vector is. Head minus tail. Okay, let's have a look at this shape. This shape is actually a square. I probably should have said that. It's a square, by the way. Okay. So that means my vector DC is equal to vector DA times I. Because if it's a square, I've rotated it 90 degrees. I haven't changed the length of the vector because the sides of a square are equal. So therefore, if I want to work out C, I can say, well, hang on, DC, that's head minus tail. Well, I know D's the number 1. So C minus 1 must equal, well, DA, head minus tail, will be omega minus 1, but times I. So now let's make C the subject, and we have an expression for the complex number C. Okay, let's now work out B. B, there's different ways I could do this, but the first way I'm going to try is I'm going to add to the point, so that's why it's just A, it's not the vector DA or anything, I'm just adding to the point A, the vector DC. Now I know the point A is omega, and the vector DC is C minus 1. Head minus tail, head minus tail. But over there we've got an expression for that. We know it's omega minus 1 times I. So putting that together, I now have an expression for the complex number B. That's one way I could have done it. I could have said, to the point C, I'm going to add the vector dA. should give me exactly the same answer. Okay, well, the point C we worked out was 1 minus I plus I omega, and we're going to add dA, head minus tail. dA is omega minus 1. All right, let's play around with that, and whew, we get the same answer. There's another way I could do it. I could do it via rotation, because if this is a square, then I know the triangle DAB would be a isosceles triangle, but more to that, it's a right-angled isosceles triangle. Therefore, the length of my vector, so I'm rotating dA, the length has been multiplied by the square root of 2, because we know the sides of an isosceles right-angled triangle are in the ratio 1, 1, root 2. So the length is root 2, the rotation must be 45 degrees, or pi on 4. All right, well, let's play with this and see if we get the same answer. That's going to be times dA. So dB is b minus 1. Root 2 cis pi on 4, which I've expanded out to be cos pi on 4, plus I sine pi on 4, and that'll be multiplied by head minus tail, omega minus 1. So b will be, because cos of pi on 4 and sine pi on 4 is 1 on root 2, that'll cancel with the root 2 out the front, and I'll get 1 plus I, omega minus 1, plus 1. We're almost there, aren't we? Not quite. I mean, it is the same thing, but let's rearrange it to show it's the same thing. Expand out, tidy up, and yeah, there it is. Minus I plus 1 plus I omega. They all work. Comes from the 2000 paper, and this time they were presented with a rectangle, told that OC is twice OA, and omega is A. Okay. First thing they wanted to know was, okay, well, what would C represent? So if I know that's a rectangle, I've got the vector OA, rotated it, well, if it's a rectangle, I must have rotated it 90 degrees, but the length of that vector, they've told me OC is twice OA. So I've doubled whatever the length is. So it must be the vector OA times 2I. The length's been multiplied by 2, been rotated 90 degrees, so we also multiply it by I. So that's simply going to be 2I times omega. What complex number corresponds to the point of intersection D? And it's the intersection of OB and AC. Diagonals bisect in a rectangle. Okay. Therefore, D is the midpoint of AC. It's also the midpoint of OB. But I'm not going to use that because I don't know what B is yet. I do know what A is and C is, so it makes more sense to do it that way. So the midpoint of AC, midpoint. So I'm now talking about the points A and C. So it'll be A plus C divided by 2. So omega plus 2I omega divided by 2. However you want to write that. I've factorised the omega out and written it as half plus I times omega. Here's another example. We have an equilateral triangle. Length of the sides is 1. We're going to find, an OBCD, is a square. We want to find B, D, and C, and I think there's a clue in the way this question is written. You've got to ask yourself, why did they say find B, D, and C? That's not normal. I mean, normally you would say, find B, C, and D. So it's sort of telling me, hey, find D before C. It's probably going to be easier. Yeah. So giving you a little hint there. All right, let's find B. It's an equilateral triangle. So I know when I rotate OA, I've rotated it 60 degrees because it's equilateral triangle. Again, the length hasn't changed because all the sides are the same in an equilateral triangle. So it's going to be OA times the cis of pi on 3. OA, they haven't given me any points. But they have told me that it's an equilateral triangle of length 1 unit. Therefore, A must be the point 1. So it's okay. We'll know it's 1 times the cis of pi on 3, and we can actually work that one out, can't we? Because we've got some exact values there. It'll be a half plus root 3 on 2I. Okay, so there's B. D. Now I see why we find D next, because now I'm just going to rotate that 90 degrees. So it'll be OB times I. I suppose I could have also done it by saying I'm going to get OA and rotate it, what would that be? 90 plus 60, 150 degrees. Either way, we'll end up with minus root 3 on 2 plus I, or half I, plus half I. Okay, C. How could I get C? Again, I've got several ways I could approach this. Which way did I go? I said from the point B, I'm going to add on the vector OD, and then it should take me to C. I didn't say it was going to be nice, but there it is. B, we said, was a half plus root 3 on 2I. OD is, well, same as the point D because it's joined to 0. So we get minus root 3 on 2 plus a half I. There it is in all its glory. So what are we being told here? We've got A and B, there's Z1 and Z2. We've got some triangles there, and they're both right-angled, or right isosceles triangles, so right-angled isosceles triangles. Part 1, explain why P corresponds to the complex number 1 plus I Z1. So what have we done? We've now got the vector OA, AO, not OA. Well, you always rotate at the tail of the vector. So I'm not rotating the vector OA in this case, I'm rotating the vector AO. You should rotate at the tail. But also, we're rotating clockwise instead of anti-clockwise. So the angle then would be minus pi on 2 instead of pi on 2, and cis minus pi on 2 is negative I. So P minus A will be negative I O minus A. So P minus Z1, there we go, make P the subject. We get Z1 plus I Z1. They said explain why. Oh, well, factorise it, and we've got what they're looking for. So now we go to part 3. There's a missing part 2. All right. I think part 2 was probably this, because looking at what they want us to do for part 3, it sort of makes sense that we work out what Q is, doesn't it? So I'm assuming part 2 was work out what Q is. So this time, how do I get to Q? I'm rotating at B, and this time, hang on, yeah, that one's anti-clockwise, isn't it? We're going from there. Yeah, anti-clockwise. So that is multiplication by I. All right, so same idea, Q minus B equals I, O minus B. So B minus IB, we get 1 minus I Z2. Okay. M is the midpoint. So it'll be those two added together, divide by 2. I mean, how do you write this final answer? Because you say, oh, let's break it up in the real and imaginary, but you haven't really, because Z1's got in the real and imaginary part as well, and Z2. However you want to leave it. I just out of habit did break it up into what looks like real and imaginary, but it's not really.